Okay, let us start then. Yes. Let me know what simulation softwares you have done up till. Simulation softwares. Can you hear me? Yes, answer please. Aura, yeah,
Sir, wait.
no. Which simulation softwares you have done up till?
Just simulation.
No? Spice or reality spice,
Yeah,
reality
we have done
sim,
Peace Price.
uh,
We have done Peace Price.
then reality sim or Proteus,
Proteus, we only did a little bit for 1 month before the
PCB,
pandemic.
PCB wizard.
No, not that.
So, okay, MATLAB you must have done, no?
Yes, sir. MATLAB we have done.
MATLAB and the Simulink, then
No,
LabVIEW,
Simulink, no.
LabVIEW you have done.
No.
Okay. Uh, this experiment is on signal conditioning once again, second chapter. The earlier two experiments were based on first chapter. Now this is based on second chapter. Okay. And consists of an instrumentation amplifier, designing an instrumentation amplifier, okay, and simulating it. So today, during this practice, we'll be doing design part, the theoretical design part, and the simulation part we'll do in the next practical. So how the instrumentation amplifier is designed, okay, for a particular gain. So design of variable gain instrumentation amplifier is the title of the experiment. Then. Okay. So let's do the theoretical design today. And if you are aware with any of the simulation software, you simulate it and you can come up in the next practical. Or otherwise, uh, I will give the software and then we'll do simulation in the next week. Okay. Better way if you know any simulation software, you put it onto it, the circuit onto it and simulate it. Okay. So let's start with the simulation software. Okay. Rather theoretical design, not simulation, theoretical design. Have you done theoretical design of instrumentation amplifier last like a DLIC? Must have studied instrumentation amplifier there, no? Have you studied instrumentation amplifier in DLIC?
Yes, sir. We have.
Uh, so that same design is to be repeated here. Okay, variable voltage gain instrumentation amplifier is to be designed. Okay, so there should not be any problem in understanding the design. As far as the instrumentation amplifier is concerned, what are the characteristics and features rather of instrumentation amplifier and what are the applications? Instrumentation amplifiers are made up of op-amp. Generally, the popular circuit is three op-amp instrumentation amplifier, right? So, what are the features of three instrumentation op-amp? First thing is that it is a differential amplifier, right? Uh, difference of two input voltages is amplified. Okay? And where this difference comes, this difference, where it is used in the industries, it is used for measurements, right? So the instrumentation amplifier inputs, two inputs come from the bridge generally. And where is the bridge input? It comes from sensor. The sensor is a part of one of the arms of the bridges. As the sensor registers or sensor parameter change, bridge output changes, and this change is a differential output VA minus VB. Thus, this VA minus VB is applied to instrumentation amplifier. Do you understand this concept then? Okay. Why instrumentation amplifier is important? Because the outputs of the sensors or the bridge, okay, are very small. And if very small outputs are there by amplifying, the output of the sensor should not be distorted, they should not have some common mode signals and all. So it should not purchase any noise as such. When we are giving this to further stages like microcontrollers or ADCs, okay, that is the next stage of after the amplification. It goes to ADC or microcontrollers. So when it reaches ADC or microcontrollers, it should not purchase any noise. Otherwise, the noise also will be processed and process, etc. Whatever the calculation is done by the microcontroller will be wrong, and our output, the control process will be wrong then. Okay? What we want to control will not be exactly controlled. That's why this stage of amplifier is very important, and instrumentation amplifiers are so important in industries and the measurements. Okay? So special features, any one of them, I want to hear from you. Any one feature of the instrumentation amplifier. As I said, it is constructed, it is made from op-amp. You may tell me the op-amp features also, one by one. Any one. Yes, it has very high input impedance, correct? Op-amp, and therefore the instrumentation amplifier has very high input impedance. Okay. Next, you must have heard of CMRR, you must have heard of the slew rate, and all these characteristics of op-amp, and they are also applicable to instrumentation amplifier also. So instrumentation amplifier is a circuit that is practically used in the industrial environment or measurements of the low amplitude signals, amplifying the low amplitude signals, because it has very high gain, open loop gain, closed loop gain, open loop gain, then it has very high common mode rejection ratio, it has very high input impedance, with high slew rate, and so on. Of course, that depends upon what type of instrumentation amplifier are constructing. Okay? So we can construct the instrumentation amplifier, three operational amplifiers using LM328, LM324, or 741 series. Okay? These are the discrete components of amps, or instrumentation amplifiers. Okay? Instead, we can have uh, monolithic ICs of instrumentation amplifier available. What are they? Some examples are AD628, then INA106, and so on. So instrumentation amplifiers are also available in ICs directly. But the disadvantage of the monolithic ICs using these will be their gain will be constant. Okay? Using a ready-made IC for instrumentation amplifier, the advantage is that all the resistors or whatever are the components used will be matched, right? They will be exactly matched. It will be very difficult in a discrete component circuit, right? So the advantage is that everything circuit is perfectly matched, but the disadvantage is that the gain will be fixed. Okay? So if we want a variable voltage gain amplifier, okay, we must use op amps. So the op amps may be 741, 741, then can be 11th, 328, 324, and so on. Okay, so, so let's see the circuit for instrumentation amplifier. This you have already done, and we are just repeating it. We are deriving the expression for first the gain of the instrumentation amplifier, and then we will be designing it for a particular gain. Right? Let's derive the expression for gain then. Okay. Let me present the screen and let's start with derivation of the gain. Okay. Okay. Can you see this screen? Is the screen visible?
Yes, sir.
Okay. Just we will derive the today we will do only theoretical design, and next time we'll be trying to simulate it using some of the simulating software. Right. So let's start with this picture. Design of variable gain instrumentation amplifier. Okay. Uh, let's see the requirement of an instrumentation amplifier. It's a very important component of industrial measurements. The temperature, pressure, flow, humidity, whatever the quantity is to be measured, it is first sensed by the sensors. Right? First stage is the sensors. Sensors like RTDs, and thermistors, and thermocouples, and strain gauges, load cells, and all these. And these sensors are put into a bridge, one of the arm of the bridge, and then the differential output across the bridge is taken. As the sensor changes, this differential output changes. This is given to the instrumentation amplifier specially. Okay. So what are the requirements of this instrumentation amplifier then? Characteristics required for this instrumentation amplifier. It should have precise gain adjustment, right? It should have very low noise. It should have low thermal drift. Its characteristics or parameters should not change with the temperature. Okay. Otherwise, if they are changing, then there will be errors in the measurement. Okay. It should have high input impedance. Why this requirement is there? Because unless input impedance is low, then the earlier circuits will be loaded. Earlier circuits are bridges and sensors. So those circuits will be loaded. So avoid the loading effect. The instrumentation amplifiers must have very high input impedance. It should have a very high common mode rejection ratio. Okay, what is CMRR? Common mode signals are those signals which are present equally at both the inputs of the amplifier. Okay. Differential inputs are V1 minus V2, whereas common mode signals are V1 plus V2 divided by 2. Right? So common mode signals are harmful because what they do, they generally distort. Okay. Unnecessarily they are amplified and they will distort the output. Okay. So common mode rejection ratio should be very high. How is the common mode rejection ratio given? It's differential gain AD divided by common mode gain AC or ACM. Okay. CMRR is given by AD upon AC or AD upon ACM. Okay. So this CMRR should be very high. So common mode signals should not be amplified. If they are present, where from these common mode signals come? They generally come out of power lines, power supply lines, which have 50 hertz frequency signals. Then various instruments or various devices are there operating or working in the industries, and these also radiate some, they generate certain interference of various frequencies. Okay, so these signals are present and they will be present equally at both the inputs of the amplifier. Okay, so they will be applied to both the inputs of the amplifier. So they are called as common mode signals, right? Whereas the differential signals are those what we are applying from the sensor or bridge. Okay, so bridge signal which is coming from the bridge is the differential input we are providing, whereas the other signals present are common mode signals. So these common mode signals should not be amplified; they must be rejected, and the parameter that measures this common mode rejection is common mode rejection ratio. Okay, so CMRR given by AD upon AC of AD upon ACM. Okay, then it should produce high slew rate. What, what is the effect of low slew rate? Okay, the signal output signal will be distorted. Okay, if suppose we have a square wave signal, its output is say 10 millivolt. Slew rate is say 5 or microvolt, 5 microvolt per second or something like that. So this due to this low slew rate, what will happen? Output signals will be distorted. Okay, so slew rate should be very high. Low power dissipation. Of course, this is the requirement of any of the electronic device, so that the instrumentation amplifier must also have the power dissipation. And the most important thing, the feature should be requirement is easy gain adjustment. Gain adjustment should be very easy. Rather, if we have only one resistance of potentiometer, so we must be able to rotate that potentiometer and gain must be adjusted. It should be so easy to adjust gain. These are the requirements of instrumentation. Okay. So this is the configuration of you are familiar with this already in DLIC installed on 3 op amp instrumentation amplifier, right? So this is op amp 1, this is op amp 2, this is op amp 3. Okay, so this is R1, R2, R3, R4, and this is R4 and R4, R5, and this is mistakenly written. This is RG. Okay, this resistance is RG, which adjusts the gain, right? So this is the main resistance which adjusts the gain. So let us derive the expression. Can you hear me? Are you there? No? Are you listening?
Yes.
Yes,
Yes.
sir.
Okay. Okay. So this is the first op amp. This is the second op amp. This is the third. This is the input VA and VB coming from the bridge. Okay. VA and VB are coming from the bridge. So these two are used in non-inverting mode, as you all know. Okay, this op amp is used in non-inverting mode. This is also used in okay. So let's start then. What is the output voltage? Suppose we know this voltage and this voltage. Okay, voltage in the input of this amplifier is known. Okay, say here the input is VB dash and here the input is VA dash. So this is VA dash here and this is VB dash here. Then output here will be, what will be? U is equal to R2 by R1. Okay, R2 by R, because what we are considering is R3 by R4. R4 by R3 is equal to R2 by R1. This is R2. R2 by R1 is equal to R4 by R3. So under this condition, the output of this will be R2 by R1 into VA dash minus VB dash. This is VA dash and this is VB dash. Non-inverting and inverting amplifier, right? Terminals. So This will be the output when the inputs here are known. Okay, and in this case, I want this current because this voltage is VA dash I have assumed, and this as VB dash I have assumed. Okay, so what will be IG? IG will be this voltage minus this voltage divided by RG, right? VB minus VA divided by RG. How is it VB minus VA? Why I have assumed this voltage as VA and this voltage as VB? Because I don't know this voltage. Na? I have assumed this is VB dash and this is VA dash. How can I say this is VA and this is VB? It's because if this voltage is here and this voltage is here. Okay? So you must be knowing the concept of virtual ground in op amp. And further, the input impedance being very high, input impedance of the op amp being very high, what we assume that there is no current in the op amp. Okay, there is no current here in the op amp. Therefore, this voltage and this voltage is same. So whatever is VA here is same VA here. Okay. Similarly, whatever is VB here, same as VB here because input impedance is very high. It acts like open circuit. If it is open circuit, this voltage is equal to this voltage. This voltage is equal to this voltage. And by that concept, this voltage is taken as VA, this voltage is taken as VB, and therefore current IG through RG is given by VA minus rather VB minus VA. I have considered direction downwards, so it is VB minus VA divided by RG. So IG is found out, right? Now, uh, since there is no current inside, so there will be no current here in this also. So this being open circuit, I these all resistances will be in series and carrying the same current, right? Carrying the same current. Okay. So if they carry the same current, R4, R5, right? So this should be R5 and R6. This should be no. So notations, you please understand. I may have given wrong notations. This is R1, this is R2, this is R3 and R4. This I have taken R4. Instead, R4 should be RG. This is R5 and this is R6. Then. Okay. Anyway, uh, please understand this. R4 is RG, this is R5 and this is R6. So VB dash minus VA dash. This voltage minus this voltage. Okay. Current IG into total resistance R4, R5, R6. That is, this is RG, R4 is RG. So R5, RG, and R6. Okay. If I consider these two resistances to be equal, R5 and R6 to be equal, then R5 is equal to R6 will give VB dash minus VA dash is equal to IG into 2R5 plus RG. Okay, all the concept is based on the fact that this voltage and this voltage is same, this voltage and this voltage is same. They are coming here. There is no current through this. All these resistances are in series and carry the same current IG, right? So this is the concept on which this equation is based. So VB dash minus VA dash. VB dash is the output here of the first op amp. The VA dash is the other output of this op amp, and then VB dash minus VA dash will be IG into 2 into R5 because we have considered these two resistances to be equal, this and this resistance to be equal. So they will be added together 2R5 plus this RG. So VB dash minus VA dash is 2R5 plus RG. Now, I'll substitute the value of IG from the equation 1 into equation 2. Okay, and what is the result then? Substituting this here. So this expression will I will have this expression in terms of VA and VB also. So VB dash minus VA dash will be VB minus VA. Okay, let's simplify this. IG is substitute VB minus VA upon RG. So this Rg, if it goes here, it will 2 R5 divided by Rg, and plus Rg divided by Rg will be 1. So this bracket will be 1 plus 2 R5 divided by Rg. So this is 1 plus 2 R5 divided by Rg to Va minus Vb. Okay. So further, this is Vb dash minus Va dash. Once this is Vb dash and this is Va dash, and the gain of this we know it's R2 by R1, considering R3 or R4 by R3 is equal to R2 by R1. Gain of this amplifier, second stage amplifier, is R2 by R1, right? So output here will be R2 by R1 into difference of voltage at this point. The difference is Vb dash minus Va dash. This Vb dash minus this Va dash into R2 by R1 will be the output. So that output is taken here. V out is equal to R2 by R1 into Va dash minus Vb dash. But Va dash minus Vb dash minus Va dash is this value. Substituting it here. Okay. Before that, just a small thing to be understood. This is Vb dash minus Va dash. This is Vb minus Va. I can interchange them. This will be minus and this will be minus. If I make it Va dash minus Vb dash and this Va minus Vb, so both will be minus and minus minus will get cancelled. And what I get is V out is equal to R2 by R1 as it is, and Va dash minus Vb dash will be 1 plus 2 R5 divided by Rg, this factor into Va minus Vb. So this is the expression of output voltage for the instrumentation amplifier, 3 op amp instrumentation amplifier. So what is the output here? It is R2 divided by R1 into 1 plus 2 R5, this plus this, okay, divided by Rg into Va minus Vb, right? So this is the expression of the output voltage of an instrumentation amplifier. Okay, that's it. And further, have you observed that the Rg, change in Rg, changes the output? All these registers are kept fixed, suppose. R1, R2, R3, R4, R5 are kept fixed. If we change Rg, V out will change. So it means that the gain can be changed by simply changing Rg. Okay, so this Rg is simply changed, and we can change the gain of the instrumentation amplifier, right? So V out upon V in will be R2 by R1 into 1 plus 2 R5 divided by Rg. Okay, has everyone understood this expression? Please answer. Are you understanding this? Any answer? Are you listening to me? Can you hear? Vishal, Saurabh, Rohan, Sandhya, Priyanka.
Yes, sir.
Okay. Do you understand this then? Okay. Well, now let us design an instrumentation amplifier. Okay. With variable voltage gain. Variable gain. So, design of variable voltage gain instrumentation amplifier. The range of gain required is from 1 to 1000. That is given. Design an op amp or other instrumentation amplifier with varying gain from 1 to 1000. That is the given question. Okay? We want to design an instrumentation amplifier with variable gain from 1 to 1000. Okay? So once again the same thing. Here what I have done, notations have been changed. You must understand that. This is taken as R2, this is taken as R1, this is R3, R4, because I have taken them equal. So I have noted them to be R2 and R1 only. So notation slightly change here. Okay? This is R3 and this is R3. So instead of R5, this will be R3 now, right? Instead of R5, it is R3. So these both will be equal, R1, R1 and R2, R2, right? So this change you must note, okay? Or you may keep it as it is and then derive, right? So R2 by R1, R2 by R1, well, and here it is instead of R5 and R6 is R3, okay? Further, this combination is RG. This combination is RG. The RG now consists of a fixed resistor R4 and a variable potentiometer pot, okay, R pot, right? So R4 plus R pot resistance is the RG, which from which we are changing the gain of the instrumentation amplifier. Okay, have you noted the change in symbols? Okay, initial circuit we have taken this is R4 and this is R3. So I am taking R2, R1, R2, R1, R2 here because anyway they are considered to be equal, right? So here instead of R5 and R6, I have taken R3 and R3 only because they are to be equal and generally they are in the design. Okay, so R3 and R3 and RG is replaced now by fixed resistor R4 and a variable potentiometer R4. Okay, and as usual, this is one amplifier, this is another amplifier, and this one is the next stage amplifier. So this here is V1 and V2 instead of VA and VB. Okay, so uh, what is the gain of this or what is the output here? Already we have derived 1 plus 2 R3 by RG. In earlier case it was R5. Now R5 is replaced by R3, therefore 1 plus 2 R3 divided by RG, where RG consists of R4 plus R4 that we will discuss later. Okay, and gain of this will be R2 by R1. That's very obvious. R2 by R1 is the gain of second stage. And overall gain will be this into this. So R2 by R1 into 1 plus 2 R3 by RG is this one. Okay. Let us assume that the second stage has a gain of 0.5. You may consider it as 1 also, that doesn't matter. That's your design criteria. Okay. Let us assume it to be 0.5. Okay. So A2 will be R2 by R1 is equal to 0.5. If I consider one of these resistance, okay, R1 is 100K, then R2 using this expression will be 50K. So R2 and R1 are now fixed because I have assumed the gain of this stage to be 0.5. Okay, this is my design. I am assuming it. Okay, so further, the overall gain is proportional to inversely proportional to Rg because Rg is the denominator. As Rg increases, A1 decreases. Rg decreases, A1 increases, and therefore overall gain also A1 into A2 will also change. Right? So there will be two extreme gains. What we are designing for 1 to 1000. So minimum gain is 1 and maximum gain is 1000. Are you getting me? Minimum gain is 1 and maximum gain is 1000. If we want to have minimum gain, then Rg which is in the denominator should be maximum because it is inversely proportional. Maximum Rg and minimum gain. Minimum Rg and maximum gain. Right? So Rg, which is the combination of R4 plus R4. If we want minimum gain, then for minimum gain, R4 plus R4 should be maximum. So potentiometer should be at its extreme point, right? We should have full value of potentiometer added with R4 that will give the minimum gain. And for maximum gain, what should be at zero position? Only R4 should be there. So Rg is equal to R4 for maximum gain and Rg is equal to R4 plus R4 for minimum gain. So this is explained here. For minimum gain of 1, Rg is maximum. R4 plus R4 for maximum gain, that is for 1000, Rg should be minimum, that is equal to R4. Okay, so let's put the value for minimum gain then. Okay, because A we have A1 into A2. So this is A2 second stage gain, and this is first stage gain. So minimum gain is 1. 1 is equal to R2 by R1 that we have considered already as 0.5. 1 plus 2R3 divided by, this is Rg, and for minimum gain Rg should be maximum, R4 plus R4 full value, right? So simplifying this, what we get is, after the calculations, 2R3 is equal to R4 plus R4. This is the expression what we get, right? So uh, let's call it as assume that potentiometer is of 100K, a variable potentiometer that consists of Rg. Assume it to be 100K. Okay? So if it is 100K, then R4 plus R4, meaning R4 plus 100K is equal to 2R3 will be equation number 1. Now let's again repeat it for maximum gain. For maximum gain, the equation will be 1000 into second stage gain into first stage gain. But in this expression, now if we want maximum gain, Rg should be minimum, and the minimum value of Rg is R4, because if this is set to 0, this resistance Rg will be only R4, right? So Rg will be R4 only. R2 upon R5, R1 is 0.5 already we have assumed, and therefore solving this expression we get 1999 R4 is equal to 2R3. Okay, so equation number 2 we get for maximum gain. This is for minimum gain and this is for maximum gain. So in expression 1 we have 2R3 here and 2R3 here. So equating them, what we get is R4 plus 100K is equal to 1999 R4. So this gives me R4 is equal to 50.05, approximately equal to 50 ohm. So if R4 is known, then substituting in any one of the equation, okay, either this maximum gain or minimum gain, is 2R3, then I get R3 is equal to 50K, right? 50 kilo ohm. Substituting R4 is equal to 50, I get R3 is equal to 50K. And what we have done, we have found out R2 and R1. Okay, this is R2, R1 is 100K, R2 is 50K, R3 we have found it out to be 50K, R4 we have found out to be 50 ohm, right? Okay, and part is taken as 100K. Okay, so values are 100K, 50K, 50K, this also 50K, this is 100K, and this is 50 ohm. Okay, so these values are only to be found out then, and thus we have designed a variable voltage gain instrumentation amplifier with gain variation from 1 to 100. Okay. So this is the procedure. This is very that way very basic and fundamental. Many practical design, many more other criteria to be considered. But let's do this basic design and simulate this one then. Okay. So this circuit will be simulating, putting these values, but this is my design. Okay, note down your question. Note down your question. Okay, and your question is design an instrumentation amplifier or variable gain from 2 to 2000. And it is 1 to 1000. You will design your own instrumentation amplifier with variable gain changing from 2 to 2000. The minimum gain has to be 2, maximum gain has to be 2000. And find the values of R1, R2, R3, R4, and R5 for this circuit. Okay, and those values are to be simulated using some simulating software next time. Okay, so this is how we will be doing that experiment. Okay, let's check if you can simulate in any one of the software, download it and simulate it, and you can send it to me. Okay, or we'll do it in some other software next time. Okay, everyone understood what is to be done? Everyone understood? I'll send this PPT for your reference design. Okay, so let me type the question for you. Design and instrumentation amplifier with gain varying from 2 to 2000, right? And this is your question then. Okay, ISD lab experiment. There is 3. Experiment number 3. Design an instrumentation amplifier with gain which can be varied, say variable gain varying from 2 to 2000. Okay. Uh, the question arising here is that which type of instrumentation or other op-amp should be used. If you use any one of the op-amps, you can use LM328 or 741 or something like that. Whichever components are available in that software, you use those op-amps and then design it and simulate it. Okay, is it clear what is to be done then? This theoretical design is to be implemented using software, simulated using software. Is it clear? Design a variable. Are the things clear with you?
Yeah.
Please answer.
Yes, sir.
So you will design and you will send the theoretical design to me, or otherwise I will check it next time. Each one's notebook. Putting the video on, I'll check it. Everyone's notebook whether he has designed it or not. Okay, in your own handwriting, not anyone other's copy. Huh? Okay. So I will share this for your reference. Okay, I'll share this presentation for your reference. Whatever the steps are, right? Okay. Any doubts about this one? Then?
No, sir.
Okay. Then let's wind up our session here. Then next time we'll be simulating this instrumentation amplifier with variable voltage gain. Right. Let me mark the attendance. Half the people are not there. Only 29, 28 people are there. More than half are absent. Okay. Further, during this week or up to next practical, I'll be sharing the drafts of the write-up of first and second experiment. Okay. Let's see how to write it and so because at least you have to write it, okay, on the notebook and present it. Okay. Whatever the screenshots or so that we have done with the Shinde sir showed to you. Okay, those screenshots you print it and attach it to that one. Okay, so I'll share the draft also of first and second experiment, and this third you have to design it. How to write it again? All 1 to 3 experiment drafts I will share with you. Okay, write up and share with you during the week, and the next week you have to show me or submit the first and second experiment, and simulation of the third we will do next time. Okay, so at least theoretical design you should uh, write in your notebook. Okay,
Okay.
screenshots.
So we have to make a separate book or in any book will do because we have to take PDF to upload it, right?
Yeah, make a separate notebook, no small notebook for this one. Okay, there will be 6 to 8 experiments in this one. Okay, maximum 8 experiments will be there. First is the pneumatic circuit, then hydraulic control valves and circuits. Then this instrumentation amplifier might be a stepper motor control. Then let me see what. Let me show you which experiments can be performed. Probable list. That's not confirmed because uh, we don't have the lab with us. So which experiments can be performed? So that's why I can't confirm. As we proceed, let's see which experiments can be performed one by one. Then list of experiments. I'll show you a list of experiments and let's see which experiments will are covered till and then which will be covered later. Let me share the screen again. I'm sharing the screen once again for you. Okay, there was a okay. The list of experiment. Yes, this is the list of experiment. The suggested list of 12 experiments. We will be taking 6 to 8 of this one. Okay. Study of pneumatic single acting and double acting cylinders that we have already taken. Study of hydraulic process control valves and circuits that is also covered. Design of stepper motor interface circuit and controllers that let us see. Then design of instrumentation amplifier with for variable voltage gain that today design and next practical will be simulating it. Signal conditioning circuit for LDR, thermistor, RTD or strain gauge. Okay. Design of linearization circuit for transistors. This pure tuning experiments will be doing using MATLAB and simulating. This experiment will be performing. Okay. Then PLC ladder will be designed. Okay. Which the PLC and ladder. One experiment on PLC. One experiment on PLC, one experiment on PID, then some simple process using lab view. Will it be possible or not? I don't know because lab view we have in college. Here is it possible or not? Let's see. If yes, if it is possible here, we will take one experiment on LabVIEW, and there will be a study experiment on SCADA or DA, that data acquisition system. Okay, not all 12. We will consider 8 experiments or something like that. Okay, so these two are already covered, and this is covered today, right? So we'll try to do this then. Is it okay? Yes. Then thank you then. So next time. Okay. I'm ending the meeting. Thank you very much.